Hello one and all, I'm going to start trying to expand my videos into the physics realm a little bit, so we'll see how it goes. So the first thing that I wanted to talk about are vectors, just a basic introduction to what is it, a vector. Well, a vector, by true definition, is something that has both a direction and a value. So things like if you are walking that way, that's a vector. If you say that you walk 10 meters that way, it's a vector. It has both a magnitude, translation number, and a direction. So from here on out, anything that has both a number and a direction, we are going to call a vector. We usually indicate this above the symbol we're talking about. For example, acceleration is a vector, and we indicate that by drawing a little baby vector above the symbol. Velocity gets a little vector symbol. In print, sometimes you will see the letter just bolded instead, but I like the little hat because that's indicative no matter what form of communication you are using. But then you might ask, what do I call just a plain number then? Sometimes you'll hear it called just a magnitude, but more often than not, it's called a scalar. And that's just your number. So things like speed, time, those are scalars. It is just the number. All right, so what happens when I have more than one vector? How can I combine these things together? So first, let's look over here and talk about adding vectors. And it should be about what your brain is probably already telling you that you should do. Is we're going to take these vectors, put them head to tail, and add them together. In this case, I indicated the length of both of them right there. Since they are both going in the same direction, that makes this pretty darn easy. So there we have it, a 1-inch vector plus a 1.5-inch vector will equal a 2.5-inch vector still going in that right-hand direction. Pretty simple, right? Subtracting vectors, you still see that? Yeah. Should be equally simple. I'll redraw them down here for you. Since they are going in opposite directions, you guessed it, we're going to draw them in opposite directions. Again, still head to tail. I'm actually going to draw them one below the other here, like this, so you can see it a little bit better. So, for example, if we walked 1 meter this way and then walked 1.5 meters back that way, overall, my resultant vector, that's what your answer is called, is going to be 0.5 meters to the left. So adding and subtracting vectors should be a pretty straightforward concept, at least visually like this. Or you can probably do it in your head simply because it is about what your brain would tell you. However, let me point out the importance of defining direction. And this may seem like a small, relatively blasé idea, but it is huge. The beauty of physics is that I can define any direction as positive that I want, or that will make my problem easier for me. Sure, there are conventions that you can follow, but overall, it's totally up to you. So before you begin any problem, I highly recommend that over in the corner somewhere, you put some kind of symbol to indicate what you are defining as positive, negative, etc. By convention, it's exactly what you would expect. Where up is positive, to the right is positive, to the left is negative, and down is negative. Again, these are conventions. I have been known to invert these completely and totally if it's going to make the math in my problem easier, but I have to indicate that in my problem before I begin. The way that I do this is I usually put something like that in the corner of my problem before I begin. You could even define right, too, if you wanted. Just to make sure that you, your reader, and everybody else are clear which direction is positive and which direction is negative. You'll notice I include up, down, and left, right And the reason for that is you need to be very, very careful to only add or subtract one axis at a time. So that means that you take care of everything along the x-axis, then completely separate in a totally new setup, take care of everything in the vertical axis. Do not combine them until the very, very end. This is huge. You will save yourself much time and frustration and general angst if you remember this little tidbit. All right, so what does that mean? What does that look like? So, when I've got vectors going in two different directions, we can look at it two different ways. We can look at it mathematically, or we can look at it visually. So, here's our first example. Notice I have both a number and a direction since these have angles. I have indicated the angles. Typically, they will always go from the zero mark, from the zero line, if you're thinking about a regular old coordinate plane. With this is 0, your values will go around there. I tend to transform them into that if they are not given to that particular convention. I will fix that myself. You'll notice that while this vector only has an up and down portion, since this is at an angle, it has an x piece and a y piece, a vertical piece and a horizontal piece. So we're going to have to make sure to address each of those separately. Visually, I can take care of it all at once. And the way that we do that is called the complete the box method. This is going to run into itself, so I apologize. And all you're going to do is create a mirror image of your arrow here. We put them tail to tail. We create a mirror image of the lower part of my box. We create a mirror image of the top of my box. And then we will draw our resultant vector from corner to corner. And there you have it. The math is a little bit more difficult because we have to bring in some trig stuff. In case you forgot, basic trig functions. We have an x side, a y side, and a hypotenuse. If I'm talking about this angle here, I can talk about cosine, sine, or tangent. Cosine is x over hypotenuse, sine is y, and tangent is y over x. How do I remember all that, you ask? Well, I have this wonderful little phrase that has stuck with me for ages and ages and ages. That's SOHCAHTOA. Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. Typically those are your xy's, which is how I wrote them here, but this is your best friend. Some of you may have the saying, oh heck, another hour of algebra stuck in your heads. That always confused me because I never remember which one was first, sine, cosine, whatever. So I like SOHCAHTOA. Alright, so to mathematically calculate this bit here, you'll notice that that 1-inch vector made this beautiful triangle. Okay, and this was 45 degrees. So we're going to use cosine to come up with the x piece and sine to come up with the y piece. So we're going to have to solve for it. So cosine of 45 equals x over 1. I'm going to have to solve for x. Means I multiply both sides by 1. So x is 7.07. To come up with y, I'm going to have to do sine. So sine of 45 equals y over 1. It's nice and simple again. It's going to be the same thing because this is a 45, 45, 90 triangle. Now comes the piece that I mentioned before. The fact that you need to make sure that you only add one direction at a time. If I look at this vector here, it only has a y piece. So y equals 1. in this case. So I'm going to add my y's together. I didn't leave myself near enough space here. I apologize. I'll call it yt 1 plus 7.07, or 0.707, sorry. X, this has no x piece, so this is just x equals 0. So 0 plus 0.707. Now I can finally combine them. To put these two together into my resultant, I'm going to use an old friend that I'm sure all of you are well familiar with by now, or at least I hope so, and that's our Pythagorean theorem. So I'm going to sub in my y and my x values. So let's see, 1.707 squared plus 0.707 squared, square root the whole shebang. Pardon me while I plug this into my calculator. Gives me a magnitude of 1.18, but I still need my direction. I need an angle. And to find that angle, now I know the x side of my triangle, the y side of my triangle, and the hypotenuse of my triangle. So you can use any trig function your little heart desires. I like tangent or cosine personally. I'm going to use cosine in this instance. We need inverse cosine since we're looking for the angle. So we'll do inverse cosine of, we're going to do x over hypotenuse. Inverse cosine of x over hypotenuse gives us about 68 degrees. Now, I realize I went through that really fast and my work is very messy. So I must beg your forgiveness to that effect. I will do this problem much neater and much more drawn out in the next video. So please do check that out if you are completely and totally bamboozled by all of this trig nonsense. Again, Mozawaki Marasen, please forgive me for that, and I will go over it in more detail in the next video. See you then.